All right. Good morning, everyone. Welcome to Peter Attia's thesis defense. So I have the honor of introducing Peter. I will just start with how we got involved in all of this degradation stuff. Peter was taking Math Sci 303, which he taught previously. I think was the first year I was first year. And I think afterward, Peter said, "Oh, really would love to work on battery degradation." And I think I said, "Yeah, that's not. It's a very difficult subject. Probably you never see the end of it." So, but Peter persisted and he says, "Okay, I'm going to work on degradation. I'm going to pick a hard problem to contribute to." So you'll see a little bit of that today. So that's the first indication of Peter's persistence in the solving problem. But then the other thing I don't like is don't work on things that's playtime, right? So then a couple years later, then Peter said, "Oh, let's work on something between batteries and AI and machine learning." I said, "Okay, that sounds probably nothing good can come out of that either." But again, Peter persisted, and actually that turned into a massive effort today that is becoming very central to all of our research going forward. So in Peter's talk, he will highlight both the fundamental aspects of learning about degradation and also scaling up a little bit more to think about from the top down what the role of informatics might be. So he will go over a couple of these, and in the talk I hope you appreciate as much as I did Peter's effort on sort of linking the material science aspect, the data science aspect, and the engineering aspect back. So I think it's well on its way to make substantial impact in the community. And with that, Peter, the floor is yours.
All right, thank you both for the introduction, and thank you all so much for coming. Today I want to tell you a bit about the work that I've done over the past 5 years on understanding battery degradation. Modern life critically depends on energy, and high energy use is associated with high quality of life. The challenges are sourcing of energy. Today, fossil fuels like coal, oil, and natural gas make up over 80% of our energy supply. Now, of course, there are some major concerns with burning fossil fuels. First is that fossil fuels are often held in countries that aren't very friendly to us, and our reliance on energy sources held by other countries is really a threat to our national security. Burning fossil fuels also contributes to air pollution, which causes respiratory illness. In many places around the world, poor air quality is really a public health crisis. And the mortality rate from coal is 1,000 times higher than that from other sources like solar and wind. And last is climate change, which really needs no introduction. The estimated global cost of climate change is $1 trillion a year by the end of the century. In many ways, climate change is a challenge for generation. Fortunately, there's good news. The levelized cost of solar and wind has dropped significantly over the past 10 years. There are still some challenges. We can classify modern energy use into two sources, grid-connected and mobile. For grid-connected, we need a way to store energy when the sun isn't shining and the wind isn't blowing. For transportation, we also need a way to store energy on the go. Here's where batteries come in, and specifically lithium-ion batteries. Again, we have more good news. Even since the time I started grad school 5 years ago, the cost of battery technology has increased substantially. But it's still too expensive when compared to solar and wind. We have a few challenges. For grid storage applications, we really just need to decrease the cost. For electric vehicles, however, we need to both decrease the cost and increase the energy density. So our main goals are cost and energy density. And most of the academic battery community has been focusing on developing new battery technologies to improve the energy density. And without a doubt, this is really important work. But I think there are also a few other knobs that we can turn to affect the cost and energy density that may be a bit easier than developing new chemistries. First is power density. And in this context, it basically means fast charging for electric vehicles. If we have faster charging, we can spend less on charging infrastructure because peak demand is lower. We won't have people sitting around for hours waiting to charge. We can also increase the effective energy density with faster charging. If we have fast charging infrastructure available, we can get away with smaller battery packs. The second is lifetime. Now, obviously, a higher lifetime could lead to lower cost because you won't need to replace your batteries as frequently. We can also trade off lifetime for energy density. Basically, if we have high lifetime and low energy density, we can change how we use our battery to achieve lower lifetime and higher energy density. And in my work, I'll be focusing mostly on power density and lifetime. So to understand how we make better batteries, we first need to understand how batteries actually work. Batteries operate by explaining the potential difference between two electrodes. The electrode is basically an array of particles on a piece of metal foil. The positive electrode isn't really standard in today's batteries. We sort of have this alphabet soup of different positive electrode chemistries. Each of them have different pros and cons, but I won't talk about this too much here. The negative electrode for almost all batteries in use today is graphite. People are trying to make new negative electrodes, but for now, graphite dominates. Graphite and other carbon electrodes are the focus of my work. I'll be showing these graphics a lot like this, but this image gives a sense of what a real graphite electrode looks like, taken from a real battery. We also need a way to electronically connect these electrodes, so we'll add in an external circuit. And next we need a medium for lithium ions to move between the two electrodes. For that we use an electrolyte. A standard battery electrolyte contains a salt and a mixture of organic solids. And to prevent the electrodes from touching and squeeze under pressure, we add a separator. It's basically made of plastic shopping bag material. Its job is to allow ions, but not electrons to stick through. So this is roughly how a battery works during charging. Both lithium ions and electrons move from the positive electrode to the negative electrode. So in studying graphite, the key thing to note here is that charging is graphite lithiation, or lithium insertion. And during discharging, the opposite happens. Both lithium ions and electrons move from the negative electrode to the positive electrode. Discharging is graphite delithiation, or lithium extraction. Now, batteries are electrochemical devices, so electrochemistry is one of the key tools that I use in my work. This is a plot of voltage versus capacity for the graphite electrode. It basically plots the energy per lithium ion, which is the voltage, versus the number of lithium sites, which is the capacity. You'll notice that there are both steep parts of the curve as well as really flat parts. The flat parts are phase transitions between different lithium graphite phases. As we add more lithium to graphite, the lithium inserts into every fourth layer, then every second layer, and finally every layer. The plot I just showed is for 10-hour charging. As we charge faster and faster, we're unable to insert the same amount of lithium into the graphite, so the capacity decreases. Commonly expressed in currents and rate in terms of a normalized current called C rate, which is the rate required to charge in 1 hour. So to make things more intuitive, let's draw an analogy to a reservoir. The capacity is basically the volume of water the reservoir holds. The voltage is the potential energy between the top and the bottom of the reservoir, which is basically controlled by the height. And the current is the flow rate, or the rate at which water flows between the two electrodes. And finally, the curves I showed were for lithiation, which again is graphite charging. The red curves here show the same trend for discharging. And a battery charges pumping water up the hill, and discharging is letting it fall back down. The second plot I want to talk about is discharge capacity versus cycle number. This is for a full cell, aka a real battery. Each of the voltage curves on the left is basically a single point on the right. Now, a key term we'll be using is cycle life. Cycle life is defined as the number of cycles for the discharge capacity to fall below some threshold. In this case, 80% of nominal capacity, which is the x-axis. In other words, the cycle life is the point at which the battery is. So as it turns out, most battery degradation is on the graphite side, especially during fast charging. Now there are a lot of different battery degradation modes, but I only want to focus on 3 of them here. The first is growth of the solid electrolyte interface, or SEI. It grows on the surface of the graphite particles. It consumes active lithium and reduces the overall capacity of the battery. Lithium plating occurs when lithium deposits on the surface of the graphite electrode instead of inserting inside it. Lithium plating is especially common during fast charging. It not only consumes lithium itself, but also provides more exposed surface area for SEI growth. An electrode deactivation occurs when graphite particles lose either ionic or electronic contact with the rest of the electrode. But there are a lot of challenges to better batteries, but I want to focus on 2 of them today. The first is the multi-length scale challenge. When we look at a real battery, we have atoms, we have particles, we have electrodes, and we have cells. And all of these different length scales are graded in different ways. The degradation modes I just described operate in length scales ranging from angstroms to centimeters. And understanding degradation over 8 orders of magnitude in terms of length scale is really challenging. The second is long development times. Having to work through chemistries in the lab, testing the cells, and then developing a new manufacturing process is really a massive barrier to battery development. So the goal of my work is to understand and improve battery lifetime on all length scales of the battery. In part 1, I'll present a model system approach to studying SEI, which is the most common battery degradation mode. In part 2, I'll present a study looking at degradation of a commercial battery on the device level. And finally, in part 3, I'll present a new approach using machine learning tools that helps us improve cycle life, without requiring us to perfectly understand how the battery degrades. The goal of this work is to reduce the long battery development times. So we'll start with the model system approach. Here my goal is to characterize and understand SEI growth on carbon black. The length scales here will be from atoms to electrodes. I want to start by talking about corrosion. We're all familiar with corrosion of common metals like iron and copper for everyday life. Corrosion is a big deal. The estimated global cost of corrosion per year is $2.5 trillion. Now, the rust reaction involves iron reacting with oxygen and water. This reaction occurs because there is a thermodynamic driving force for the iron to oxidize and the oxygen to reduce, just like there's a driving force for water to roll downhill. So some of the iron will convert and form iron oxide. As time goes on, this iron oxide layer gets thicker and thicker, which makes the iron thinner and thinner. To have more rust to form, the oxygen and water have to first diffuse through the iron oxide layer for further reaction to take place. What this means is that rust formation is a self-passivating reaction, which means that its growth rate gets slower with time. And as the layer gets thicker and thicker, it takes more and more time for oxygen and water to diffuse through the iron oxide, and thus the growth rate slows down. The general scaling relationship for this is that thickness scales with time to the 1/2. And in general, the fact that we know so much about how rusting works allows us to design ways of stopping it. Now, SEI growth in lithium-ion batteries is actually quite similar to rusting. SEI growth is probably the single most common lithium-ion battery degradation mode. I think it's safe to say that it's the biggest reason why your phone battery dies every 2 years. If we look at the surface of a single graphite particle, we have lithium, graphite, and electrolyte. Some of these electrolyte components include things like EC and LiPF6. Just like before, there is a thermodynamic driving force for the lithium and graphite to react with the electrolyte. It's a spontaneous reaction. These SEI growth reactions consume lithium, which reduces the overall capacity of the battery. Now, if we measure battery degradation during storage, we actually find that it also roughly corresponds to self-passivating growth. The capacity fade scales with T to the 1/2. But we still have some key questions about how this actually works. The first is the composition of the SEI. We really don't know what the SEI structure or composition is on the nanometer scale. The second is transport. In the case of rust, we know that environmental molecules like water and oxygen diffuse through from the medium to react with the iron. In the case of SEI, we don't know if electrolyte molecules diffuse through or if lithium ions diffuse through. And a lack of understanding is what makes it challenging to design better SEIs. So the goal of this section is to understand the microstructure, chemistry, transport, and growth of SEI. Now, there have been thousands of papers published on the SEI, but we still don't really understand it. Turns out there's a good reason, it's just really hard to characterize. So the two biggest challenges are sensitivity to ambient air conditions, as well as to X-ray and electron radiation. These radiation sources power most of the tools that we use to study interfaces. Now, Will kind of alluded to this, but when I started my PhD, I came across a few quotes that I think summarize the SEI field pretty well. Martin Winter wrote that the SEI is the most important and least understood solid electrolyte when chargeable lithium batteries. Kang Shu cryptically wrote that the more we learn about the SEI, the more we know how little we understand. And lastly, an unnamed battery researcher told me that I wish I never studied the SEI. Unfortunately, that wasn't enough to dissuade me, but clearly we need to be really careful as we approach this problem. So here we're going to use a model system. The idea behind a model system is that it has some key properties of the main material we're interested in, but also has some properties that make your life a bit easier. In this case, we use carbon black. You may not have heard of it before, but carbon black is actually the thing that colors most of the black things that we use in everyday life. Carbon black is also really small. The average particle size of the carbon black that we use is around 50 nanometers, which is 200 times smaller than graphite. The advantage of small particle sizes is that they have really high SEI growth rates. This means that carbon black is a bad material to make a battery with because we degrade it really quickly, but it's great for us because we want to study SEI growth. The structure of carbon black looks something like this. We see that it has these small graphitic domains. But what's really great about it is that it has this well-defined interface, which makes it easy to see the boundary between the bulk material and the SEI itself. And this last major advantage is solid solution lithiation. We saw a few slides ago that graphite has these phase transitions. Carbon black doesn't have these phase transitions in solid solution, and because its voltage curves are smooth, it makes it easier to analyze data. So in a lot of ways, carbon black is really an ideal carbon system for SEI studies. So we started by applying cryogenic electron microscopy, or Cryo-EM for short, to understand the local structure of the SEI. Applying this technique to batteries is really pioneered by the Sway group here at Stanford, and for this project, we're closely with Will. Cryo-EM enables atomic resolution imaging with minimal beam damage and air exposure. The idea is that if we freeze the sample, we can prevent both further reaction with air and use lower beam doses to achieve comparable images. This is critical because, again, SEI is traditionally very difficult to characterize. Just to rehash, the key features of carbon black for imaging are its well-defined interface and its high surface area. So we look at pristine carbon black via Cryo-EM. It has this nice, well-defined interface with nothing on it. I just want to emphasize here that the thin lines that we see in the particle are atomic planes of carbon, which to me is pretty remarkable in its own right. After one cycle, we start to see a thin amorphous SEI layer form. We're going to refer to this thin type of SEI around 2 nanometers thick as primary SEI. After 20 cycles, the primary SEI involves a highly inorganic structure of small crystallites of lithium oxide, lithium hydroxide, lithium carbonate. The structure had been theorized before, but with Cryo-EM we're able to directly visualize it. We also noticed something interesting about the electrodes after many cycles. We actually don't even need Cryo-EM to first notice it. If you look at an SEM image of a carbon black electrode after one cycle, we basically see what we expect. We can clearly make out individual particles. After 50 cycles, we see this very goopy stuff covering the carbon black electrode. We then looked at the electrode with Cryo-EM, and we immediately saw that this type of SEI is well over 100 times as thick as the primary SEI. For now, we're going to call this secondary SEI. And if we look more closely at the boundary between the amorphous secondary SEI and the carbon black, we see that overall it's quite clean. We don't see the inorganic components that we saw before. If we perform chemical analysis comparing carbon black to the SEI, we find that the SEI region is high in carbonates, which indicates reduction of ethylene carbonate. So if we summarize our findings of SEI microstructure and chemistry, we see two distinct types of SEI emerge. On some particles, we see this nice, well-defined primary SEI. It's only a few nanometers thick, which is good because it means it didn't consume that much lithium. After many cycles, we see a slightly thicker SEI with crystalline inorganic components embedded inside. And it's possible that these crystalline inorganic components contribute some sort of passivity ability to prevent further SEI growth. In other particles, however, we see this large amorphous secondary SEI that gets bigger and bigger with cycling. It's the fact that it's so thick means that it consumed a lot of lithium, which is bad news for battery capacity. Secondary SEI could also be a big problem for real batteries, since it blocks lithium-ion transport throughout the electrode. This reduces the rate capability, which affects things like fast charging. Now, one open question is what causes some particles to go primary SEI and others to go secondary SEI. If we can figure this out, hopefully we can design battery particles to go primary SEI instead of secondary SEI. Another thing to note is that we have a slightly different finding than previous work. Most previous work talks about a two-layer structure of SEI with a thick organic layer above a thin inorganic layer. What we find is that both of these motifs exist, but they exist on separate particles. So it seems to suggest that the two-layer model is wrong. And the fact that we're able to directly determine this really speaks to the power of Cryo-EM. So now we better understand the structure and chemistry of the SEI of carbon. But we still don't understand the transport and growth of SEI across the interface. So for this, we're going to turn to electrochemistry. Electrochemistry is sometimes underrated as an analytical technique, but I've always been somewhat enamored by it. Highly quantitative, allows for in situ measurements, and it's pretty easy to use. I don't have time to discuss the details, but I developed an electroanalytical technique to isolate the electrochemical signal of SEI from that of carbon black. I'm going to use this technique to measure electrochemical dependencies of SEI in voltage, current rate, and current direction. This plot shows SEI grows as a function of voltage. We find that SEI growth dramatically accelerates if we go to low potential during lithiation. It has roughly an exponential dependence. But during dilithiation, however, the growth is near zero. I then measure the SEI growth rate as a function of the applied cell current. The left is slow cycling, 100 hours per cycle, and the right is relatively fast cycling, 5 hours per cycle. We see that SEI growth rates during lithiation increase with faster cycling. As an aside, this might be important for SEI growth during the fast charging, so keep that in mind. However, the most striking part of this result is that SEI grows much faster during lithiation than during dilithiation. This is quite surprising because the driving force for SEI growth is similar in both directions. So we'd expect similar driving forces, or we expect similar SEI growth rates in both directions as well. I really want to emphasize how striking this is. The fact that SEI goes so much more in lithiation relative to dilithiation is probably the most surprising result from the PhD. Let's explore this directional dependence a bit more. During a single cycle, the voltage during lithiation and dilithiation is similar. The electrode spends a similar amount of time below the stability window of the electrolyte. So we'd expect similar amounts of SEI in both directions. But we saw that SEI only grew during lithiation. In fact, we can see that even just from the capacity curve of carbon black. Capacities during lithiation are decreasing, indicating cell passivation. But in contrast, the capacities during delithiation are constant, which indicates no SEI growth. I also want to mention briefly that a lab mate recently also saw the same effect in graphite. So this directional dependence isn't just some weird fluke of carbon black. Now this section is probably the most complex of the three in my talk. Before we take a deep dive back into the material science, I want to translate some of the findings from electrochemical work into practical insights for taking care of batteries. So first is that you don't want to charge your battery beyond 80% stable charge. The SEI growth rate scales exponentially with voltage. So when you plug in your battery overnight, it spends a lot of time at high potential growing SEI. This is bad. The second is that you should charge slowly. Well, best case, you shouldn't charge at all, but obviously it's not really practical. Overall, you should charge slowly. And the third is that battery usage conditions really don't affect SEI growth. And this is really important for electric vehicles, since SEI growth is near zero, regardless of how quickly you accelerate. Okay, back to material science. So we quantified the SEI growth kinetics and found this very strange observation that SEI grows a lot during lithiation, but appears to be turned off during delithiation. In a way, the kinetics of SEI growth appear to act as a diode. They only work in one direction. So to better understand this, we built a model that can try to explain these results, and in particular, the strange observation of the SEI growth and direction dependence. So I worked closely with Supra and Martin at MIT to design a model that could explain this phenomenon. The model had three key features. First, we assume that SEI can conduct both lithium ions and electrons, meaning that we assume the SEI is a mixed ionic electronic conductor. For context, graphite and most other battery materials are also mixed ionic electronic conductors. So we're basically treating the SEI here as an electrode. But even though the SEI conducts both electrons and ions, the ionic connectivity is much higher than the electronic connectivity, because the timescale for lithium ion insertion is minutes, and the timescale for SEI growth is really hours, or weeks, or months. And there are two relevant features of mixed ionic electronic conductors here. They are electroneutral, meaning the concentrations of both lithium ions and electrons are equal. Another important aspect is that the concentrations are dynamic, which is important to capture this phenomenon. The second assumption is that the electronic connectivity of the SEI scales with the square of the lithium ion concentration in the SEI. Now we know that the electronic connectivity must be highly sensitive to the ionic concentration, so we build in the square dependence. This is actually a pretty standard assumption in semiconductor physics. Now the electrons are localized with other electrons as they move across the SEI. The technical term for this is actually hopping. So once the electrons hop across the SEI, they react with solvent and lithium ions to form new SEI. So now we have a mechanism for the electronic connectivity to change. But why does it actually change during lithiation versus delithiation? Again, I don't have time to get into all the details, but the main idea is that because the SEI is so thin, we assume that the lithium ion concentration in the SEI is in equilibrium with the surface concentration. This means that the lithium ion concentration in the SEI is strongly dependent on the electric field across it. The field dependence is based on the direction of lithium ion motion, which is governed by the direction of the current. So as soon as we switch from lithiation to delithiation, the double layer of the SEI electrolyte interface is depleted, and thus the SEI is depleted of lithium ions. As a result, the electronic connectivity of the SEI drops because the electrons lost hopping sense. So SEI growth ends up being much faster during lithiation than delithiation. We then developed simulations to better understand this highly complex system. We found that this type of model can accurately capture the unexpected directional dependence of SEI growth. So in this section, we first characterized the structure and chemistry of the SEI using Cryo-EM. We saw both thin primary SEI and thick secondary SEI. Second, we used electrochemistry to measure the kinetics of electrochemical SEI growth. We found this really surprising result that the SEI grows much faster during lithiation than delithiation. And lastly, we put this all into a model, which is able to explain the directional dependence. Hopefully, these insights can be used to design new electrolytes that reduce the form good SEIs. I think the biggest takeaway from this section for me is that the transport properties of SEI are dynamic. As an experimentalist, I often think my goal is to identify the most important properties of a system so that we can develop a theory around it. And there are countless SEI modeling papers, but almost all of them treat the SEI kinetics as static. It seems reasonable given how thin the layer is. But what we found here is that this assumption is way off. The kinetics are highly dynamic. I think this holds not only for the SEI and graphite, but also the SEI in silicon, lithium metal, and other chemistries as well. Let me take a quick water break. Okay, so how's my work on a model system? We're now going to move up a few length scales and look at degradation material science in the last section. Hopefully the next two sections will be a bit more accessible. Now the work in part 1 is performed in homemade coin cells. They're basically watch batteries, something like this. But the cylindrical batteries used in some electric vehicles have around 10,000 times the capacity as these coin cells. And as we move to these form factors with higher energy density, things get a lot more complicated. So for example, cylindrical cells have multiple layers coiled together in what's called a jelly roll. We can also operate these devices at realistic operating conditions, which is fast charging. We also have to consider the presence of inactive components like the electric tab. And finally, during operation, we can have a large gradient throughout the system. These gradients can be either thermal, mechanical, or electrochemical in nature. So in order to really understand battery degradation, we have to move to more relevant systems. The cells I use in my work are LFP graphite cylindrical cells. I'll be using these cells in parts 2 and 3. I'm just going to just pass a few out. Get a sense of what they're like. So these cells are actually pretty commonly used in things like power tools, electric buses. They also actually power 44% of Chinese cities. These are power cells. We're going to use them to study fast charging. Now your electrode is graphene, which again is very standard in most batteries. So hopefully these results will be generalizable to other cell chemistries as well. The positive electrode is LFP, which is short for lithium iron phosphate. The main thing you know about LFP is that it has really minimal degradation. This is actually the real reason why we use these cells. These cells are a model cell chemistry for my work because almost all the degradation in these cells is on the graphite side. Now the goal of this section is to understand degradation during fast charging. In this plot I show discharge capacity versus cycle life. The dotted red line indicates the cycle life. We started by varying the charging rate by keeping the discharging rate fixed. So here we have progressively higher C rates, which correspondingly decreasing charging times. So again, 1C is the rate to charge 1 hour. What we see here is that if we charge in less than 20 minutes, the lifetime is really good. The degradation is pretty minimal. These cells are going to last well over 1,000 cycles. If we go to 4C or higher, aka faster than 15 minutes, we begin to see much more rapid degradation. And the cycle lives begin to decrease from many thousands to only hundreds. So something weird is happening here as we go from 15-minute charging, sorry, we go from 20-minute charging to 15-minute charging. And that's what we'll be exploring the rest of this section. So to figure out what happens to these cells, we're basically going to be forming battery autopsies. This disassembly technique was developed in collaboration with Jerry, so there, who is the master's engineer. So this is the unrolled graphite electrode of the pristine cell. You see it has a really nice gold color to it. Graphite has this pretty cool property where it changes color with composition. So nelithium graphite is black, while lithium graphite is gold. So what we're going to do is disassemble the cells in the charge state. The idea is that the gold regions are parts of the electrode that are active, meaning they can be lithiated. And before we disassemble the H cells, we charge them really slowly to make sure the lithium ions have all the time they need to insert into the active regions. So here's the pristine cell again. We can see it has this really uniform color across the whole electrode. I'll briefly mention that as we move from left to right, we move closer to the center of the cell. If we look at one of the slow charge cells, like 3C, 4C, after 1,000 cycles, you see a bit of degradation on the right, but overall there's a lot of gold. That's consistent with the cycling results, where the cell seems to be lasting a while. Things are getting pretty crazy once you look at the fast charge cell. So after only 200 cycles, we see this really widespread degradation. The edges on both the top and the bottom of the electrode are almost entirely black, which again is inactive. And what's really interesting is if we look at a cell that was slow charged but fast discharged, we don't see this widespread degradation. We do see a little bit towards the center, in the middle, but it's much less than the fast charge cell. So our conclusion here is that significant electrode deactivation only occurs during extreme fast charging. So let's take a look at the cell that experienced extreme fast charging. If we perform top-down SEM of the active and inactive regions, we see that the active region basically looks like pristine graphite. But the inactive region has this amorphous goop all over the surface. We then perform tomography of the electrodes. Tomography is basically the same thing as a CAT scan. If you look at the cross-section, we again see that the active region looks pristine, but the inactive region appears to have this surface layer that extends around 10 microns into the depth of the electrode. And I'll briefly mention that we also did Cryo-EM of the surface and found that it contains some sort of electrolyte components. So it's possible that this electrolyte component was originally some sort of lithium metal, but when we measure it, it's basically just SEM. So what we can conclude is that the surface layer is likely blocking lithium ions from entering the bulk of the electrode. And this is what's responsible for the widespread electrode activation. Now, if we take a close look at the electrode after fast charging, we notice something pretty interesting about the degradation pattern. It looks like most of the inactive region is the same height as the electrode tabs. The tabs are seemingly minor quantities. They basically provide an electronic connection between the current collector and the cell terminals. There's a pretty clear relationship here between the inactive regions of the electrode and the tab location. This is reasonable. When the electrode is rolled up in the jelly roll, the tabs impact all regions with the same axial position. So the tabs seem to be exerting some additional pressure for the regions of the electrode at the top and the bottom of the cell. We then wanted to quantify what kind of pressure the tabs would have. So we're going to use tomography of a charged cell. Again, tomography is basically a CAT scan. What's really great about this technique is that it's non-destructive, meaning we can look at the jelly roll without taking the cell apart. So here we're comparing active and inactive regions, taken from the center to the bottom of the battery. And the contrast in tomography here comes from atomic number. So we're basically, the bright lines here are basically looking at the copper current collector of the battery. Now visually, these two electrodes are pretty similar except for the tab. But we can actually quantify the strains via tomography. So what we can do is take a line scan. And because the copper current collector is so bright, we can easily detect it. So measuring the copper-copper distances provides an easy way to measure the stack thickness. If we compare the average copper-copper distance for the active and inactive regions, we get a difference of around 2%. It's pretty small, around 7 microns. It's not large, but it's just significant. Now for context, 7 microns is around the width of spider silk. So it's 10 times thinner than human hair. I mean, given the length scale of the battery, 7 microns is not that big. Now, I don't have time to go through all the math here, but we estimate that the 7 micron difference in thickness leads to an additional 95 millivolts per potential. And based on our measurements from SEI voltage dependence from part 1, this corresponds to a 6-fold difference in SEI growth between the active and inactive regions. So it's reasonable here to see how small differences on the cell level can lead to large differences on the nanometer level. So in this section, we saw how SEI growth leads to widespread electrode inactivation during fast charging. For me, there are really 3 big takeaways from this. First is the importance of pressure. Battery models today exhaustively model things like temperature and cell concentration and lithium ion concentration. And most of them don't account for pressure at all. But here we see how heterogeneous pressure leads to significant degradation. So what we really need to do is to start to incorporate pressure into cell-level battery models. Then we can add in heterogeneous pressure, and then we can add in heterogeneous degradation. I also think it's shocking how these really small differences on the cell level translate to these massive differences on the electrode level, on the nanometer scale. And to me, this really highlights the challenge that battery devices have operating at so many different lengths, especially since things you don't expect to be important can have an outside role to play, they can tag. This is a major challenge for battery research. There's just so much more to think about once you go from the materials level to the device level. And lastly, I wonder if there's a simple fix to this problem, be a better cell engineer. The obvious solution here is to use thinner tabs, or shorter tabs. Maybe you could cut out the tab from the copper current collector directly. I bet there are a lot of little things we can do to improve battery lifetime on the device level that don't involve redesigning either chemistry or materials. Okay, so far we've seen how complex battery degradation can be. And hopefully you now have a better understanding of why battery development takes so long. The question is, what do we do in the meantime? This leads us to the final part of my talk, which is top-down optimization using machine learning. The goal of this work is to tackle battery challenges like fast charging, without having to really know anything about how the battery is integrated. Our goal here is extreme fast charging, or XFC. XFC is defined as charging to 80% in 10 minutes or less. SFC stands for state of charge, just a little number on the top of your iPhone or laptop. XFC is really important for a few battery applications, and particularly electric cars. The key challenge here is achieving fast charging while still maintaining high lifetime. Now, lithium-ion batteries have only been around for 30 years or so. There's actually a lot of prior work in this area. And in fact, people have been thinking about this trade-off for centuries. Dare I say light. Light seems to be done with 2 options. The first is to live fast and die young. The second is to live slow and die whenever you want. Batteries in fact face the same dilemma. Charge fast and die young, or charge slow and die quick. Our goal, of course, is to charge fast and die young. Okay, so all jokes aside, there's actually been a lot of previous work on battery degradation. A standard approach is multi-step charging. Ideas at different degradation modes manifest more prominently at different states of charge. So most of the previous literature suggests that the current steps should be monotonically decreasing to avoid the lithium plating potential threshold at high potential. Lithium plating is a canonical degradation mode during fast charging. Now, of course, the challenge here is determining the right values and locations to use for these various current steps. The number of possibilities moves up really quickly. There are two ways that people can approach this problem today: first principles modeling or empirical testing. First principles modeling is a really important part of battery research. The problem, again, is a multi-length scale challenge. We have pretty good battery models that operate on 1 or 2 length scales, but not 8 length scales. This is especially true for extreme operating conditions like fast charging. And like we talked about, important effects like pressure are often not modeled. So unfortunately, battery models just aren't good enough yet to use for optimization. The natural alternative is top-down empirical testing. There are a number of challenges associated with this. For one, there's a large number of different fast charging protocols to test. 2, there's really high manufacturing variability. So if you cycle the same cell the same way, you get something like 40% difference in cycle life. And 3rd, battery lifetime is just really long, often taking months to years for mature chemistries. So if we do a quick back-of-the-envelope calculation for a typical parameter space, we get something like 1 billion battery cycles needed to be cycled. 1 billion battery cycles means it'll take me probably another 30 years to graduate. Bottom line here is ain't nobody got time for that. So we need a faster way. Our approach is closed-loop optimization. We start with battery cycling. We then feed the initial cycling data to an early prediction algorithm, which reduces the time per experiment. We then feed the predictions into an optimal experimental design algorithm, or OED for short. The role of OED is to reduce the number of experiments, or more precisely, to intelligently recommend the next test to try. The OED algorithm then sends these tests back to the battery cycler, and the process repeats until we solve the problem at hand. To start with early prediction. The goal of early prediction is to predict the final cycle life using only a small subset of the initial data. You've seen this plot before. This is discharge capacity versus cycle number. Now, traditionally, early prediction has been a pretty hard problem. Most previous work is only able to predict the final cycle life after the batteries have already experienced significant degradation. So in other words, we're basically predicting the cycle life of middle-aged batteries. We set a goal of using the first 100 cycles, which is equivalent to predicting the lifetime of kindergarten-age batteries. So the first step in this process was setting up the cycler. We have a 48-channel battery cycler, and we cycle the cells in the temperature control chamber. We then generated a data set of 124 batteries cycled to failure during fast charging. We cycled the cells with a bunch of different fast charging conditions, but we kept the discharging conditions fixed at 4 C. What we found is that the cycle life is highly sensitive to the charging time. The charging time here varied from 9 to 13 minutes, but this formative difference in charging time has a massive effect on lifetime. So again, the goal of this work is to predict the final cycle life using the first 100 cycles. And here the cycle life ranges from 150 to 2300 cycles. Now, an important step in the machine learning approach is to generate features that we can use to build a model. So your features are just some transformation of the raw data. We started with features based on capacity. And a lot of previous work is based on the capacity they occurred because it's so easy to use. This plot shows the discharge capacity for the first 100 cycles. We don't see a strong trend with color, which implies a weak relationship with cycle life. In fact, even our best capacity-based feature has a pretty weak relationship with cycle life. The correlation coefficient of this feature is just 0.47. This was initially a pretty discouraging result because it suggested that early cycle prediction was not possible. However, if we build features based on the voltage curves, we get features that are much more predictive. This feature here is basically looking at the evolution of voltage curves from cycle 10 to cycle 100. And here we immediately see a clear trend in color. The red curves show a big change from cycle 10 to cycle 100, which suggests that the cycle life is low. And the blue curves show a small change, which has correspondingly high cycle life. If we convert these vectors into scalars using the variance function, we find that this feature strongly correlates with cycle life. Now, one thing to note is that this voltage data is relatively messy, which is why often a lot of people don't use it. They throw it away. But it seems to be the most important for later prediction. So now we're ready for machine learning. The machine learning part of this work was led by Kristen, Richard, and my team. We created 20 features based on data streams like voltage, capacity, temperature, and terminal resistance. And I've shown just 4 of these features here. Now it turns out if we build a linear model with just that single feature from the previous slide, we get something like 12% test error. Again, we're just using data from the first 100 cycles, just to the left of the dotted line here. If we compare that to our best model, we get around 9% test error. This model chose the best 9 features out of a total pool of 20. So additional data streams like capacity and temperature do seem to improve the predictions, but the primary predictive performance comes from the voltage features. The bottom line here is that we can get accurate predictions with just the first 100 cycles, which is great for closing optimization. We then want to understand why the voltage features work so well, while the capacity features work poorly. Well, from part 2, we saw how fast charging leads to significant electrode activation. This actually exactly explains why the voltage works, and not the capacity. Batteries are typically designed with more graphite sites than lithium ions. Let's imagine we lose an active site, but we still have more graphite sites than lithium ions. The capacity doesn't change, but the voltage changes because the crystallographic ordering of lithium and graphite is now different. So the voltage features from the first 100 cycles are predictive because electrode activation initially only changes the voltage, but not the capacity. So that was really prediction. I'll now move on to optimal experimental design, or OED for short. Again, the goal of this component is to reduce the total number of experiments. So again, our goal is to minimize charging time and maximize lifetime. So here we want to find the longest lasting combination of current steps that still charges in 10 minutes. This plot illustrates an example of our 6-step fast charging protocols. The last 2 steps are fixed for all protocols, which leaves 4 free parameters. However, we also fixed the charging time to 80% to be 80% state of charge to be 10 minutes. So this additional constraint means that we have 3 free parameters, CC1, CC2, and CC3. This plot shows our dependent variable, CC4, as a function over 3 independent parameters. So in total, we have a parameter space of 224 fast charging protocols. Now the key challenge for OED is the exploration-exploitation trade-off. And in fact, this is the key challenge for many of the decisions that we make every day. Whenever you decide to try something new, like a new restaurant, you risk disappointment for a chance to improve upon your current options, which in my case is very obvious. Okay, so we work closely with Attia and Stefano from Stanford Computer Science to design an algorithm tailor-made for this battery application. We use a multi-arm bin algorithm to balance exploration and exploitation. In Vegas, the slot machine is typically called a one-arm bin. So a multi-arm bin algorithm tries to maximize the total winnings over an array of slot machines. We also incorporate smoothing to account for the relationship between neighboring charging protocols. So the idea is that if we test a point over here, and it has high lifetime, it's equally likely, or it's highly likely that a point over here will also have high lifetime. This is analogous to playing Battleship, where if you get a hit, it's likely that the player next to it is likely also a hit. The last aspect is batching. We have a 48-channel battery cycler, so we test around 48 points at a time in what we call a batch. But we also incorporate feedback, so we have sequential experimentation. In our setup, we have around 200 cells in total, which equates to 4 batches. So here's a closed loop in action. We start by testing a random subset of the protocols. Again, instead of cycling the failure, we're using the predicted cycle life using the first 100 cycles. So each batch only takes around 4 days. In batch 2, we've started focusing on the most promising region of the parameter space, but we're still doing a bit of exploration. By batches 3 and 4, we're only collecting data from the most promising protocols. So we can clearly see the transition from exploration in batch 1 to exploitation in batch 4. To illustrate this a bit more, 67% of the batteries end up testing 21% of the protocols. So we're spending most of our resources testing only the most promising points. And behind the scenes, the OED algorithm is building a dynamic estimate of the parameter space. This updates the estimated lifetime of all protocols using all the data. So initially, we assume that all the protocols have equivalent lifetime. After batch 2, we've identified the most promising region. And by the end of the experiment, we just slightly modified the locations of the best points. What's pretty exciting about this is that our estimates don't change much from batch 2 to batch 4. So we may be able to cut the testing budget in half and still do pretty well. And to me, this really speaks to the effectiveness of OED. In total, this experiment took just over 2 weeks, and we used less than 1 cell per charging protocol. So this demonstrates an efficient use of both time and cells. This plot shows that we can dramatically reduce the total number of experiments required. Again, on average, we use less than 1 cell per protocol. The way we do this is by using all the data to update estimates for all of the protocols. We also never test the majority of protocols, and only a small subset are tested multiple times. Because again, we're spending most of our resources testing only the most promising protocols. Now, I briefly mentioned that we also validated the performance LED. We found that it generally captures the rankings pretty well. So machine learning obviously gets a lot of hype these days, but I want to reframe this technique for a moment as a characterization tool instead of an optimization tool, so we can learn from it. If you look at the best protocols estimated by OED, we find that this charging protocol is very close to constant current charging. This is quite different from conventional wisdom of fast charging optimization. Again, most charging protocols proposed in literature have monotonically decreasing currents to avoid the plating. So the natural question becomes, what degradation mode are you optimizing for with charging? We have some ideas, and I'd be happy to discuss them later, but what's clear here is that we're definitely not optimizing for plating. We find this pretty surprising given that plating is so widely reported during fast charging. Our best guess here is that constant current charging is an optimal strategy for minimizing heat generation. As SCI grows, it increases with increasing temperature. And this makes sense given the results from part 2. So wrapping up part 3, we've successfully demonstrated the power of closed-loop optimization for battery applications such as fast charging. With early prediction, we achieved around 9% prediction error using the first 100 cycles. With OED, we optimized over the whole parameter space in 16 days using less than 1 cell per protocol. Again, it's a combination of these two elements that makes for a unique and powerful method to accelerate battery development. So zooming out a bit, our original objectives were bottom-up approaches in part 1, device level bottom-up approaches in part 2, and the top-down optimization method in part 3. In part 1, we characterized the structure, chemistry, transport, and growth of the SCI using Cryo-EM electrochemistry. We found this really surprising result that SCI growth is much faster during lithiation than delithiation. Using this key insight, we built a model that captures the dynamic transfer properties of the SCI. Again, the main takeaway from this section is that the transfer properties of SCI are dynamic. This holds for the SCI that forms on carbon, as well as many other battery materials. On the experimental side, I think this really motivates the need for in situ and operando interfacial studies for electrochemistry, in situ AFM, and other segments. We really need ways to see the SCI in action. Thanks. On the modeling side, I think we absolutely need to understand the dynamic behavior of the SCI, as well as their dependence on potential and concentration. This seems to be the key to understanding important battery degradation modes such as SCI. On the device level, we saw how fast charging led to widespread electrode inactivation, which was caused by the presence of a large SCI layer in the surface. We had 3 conclusions. First, we saw the importance of pressure in degradation. Since pressure often is incorporated into battery modeling, understanding the effect of pressure needs to be the focus of future battery model work. We also saw how complex battery degradation can be. Small differences in stack thickness on the cell level can lead to really massive differences on the game. This really motivates the need for device level studies, since the dominant failure modes may not occur in small scale testing. And lastly, we considered how device level optimization efforts, like tab engineering, could lead to dramatic improvements in lifetime during fast charging. And lastly, we considered how machine learning methods can be used to accelerate battery development, especially given how complex battery degradation actually is. We demonstrated an efficient battery optimization method that doesn't require us to know anything about the degradation mechanisms. We saw how the combination of early prediction with OED makes for a really powerful method to accelerate battery development. We can take the closed loop a bit further by modifying the design of the battery itself based on feedback from the closed loop. And even beyond batteries, I hope this method gains traction in other settings that require many long-lasting experiments. Ultimately, I see early prediction combined with OED as really a general method to accelerate scientific discovery. So going back to our original challenges, we saw how tricky the multiple link scale within the battery can be. To get around this, I studied degradation in both model systems and real devices, in the bottom-up approach. We also considered how we can accelerate the long battery development times. Here I use tools from machine learning, artificial intelligence, to efficiently optimize battery cycle life during fast charging. I hope this works as a small step towards making better batteries, Those better batteries will lead to better equipment. Thanks for your attention.
All right, we have time for a few questions.
That was awesome.
Thanks.
You talked about fixing the tab engineering, making the tabs thinner.
Right.
I think companies are already making them as thin as they possibly can. So it occurs to me that another way to do that would just be to make the electrodes thicker in the center and thinner along the edges.
Yes, I agree.
So, don't agree yet. So my question is, what do you think are the pros and cons of that?
So thicker electrodes generally leads to higher transport over potential. So if you have electrodes that are too thick, you could have more plating, more degradation of foam. So
Let's say we just made it thinner along the edges.
that could be good. You also have lower capacity. It's also good. Again, it's all a trade-off between capacity, lifetime, whatever you care about.
Yes, for your first part, I want to know why it's surprising. So typically when you buy a battery, it's typically bought in the discharge state.
Right.
Because you don't want detected graphite, because that's the potentials are much lower, so the driving force for reaction with the electrolyte is higher.
Right.
So I wanted to know why it's surprising that there was more reaction or more SCI growth during lithiation, because you are forming lithiated graphite, which is more reactive to the electrolyte.
Right, so it's less so that's more of a state of charge effect. So we think about this animation, basically when it goes down and back up. We're spending the surprising part about it is that the potential, like the potential gradient driving force, in both directions is pretty similar in both lithiation and lithiation. So the state of charge is similar, it's sort of state independent, regardless of how you get there. But it's the location of the, or where the battery's at. That's where it should be driving the driving force. So basically, during lithiation, the battery goes down here, during dilithiation, it goes back up. The driving force is pretty much symmetrical.
Those lines you mentioned, the dynamic nature of the kinetics you're seeing for SCI growth will be similar for silicon, lithium, etc. Why do you think that? And like, do you have any
Yeah, I don't necessarily know if they translate directly from this. I think that the kinetics, the dynamic nature of the kinetics should be modeled in all of the systems.
But like fundamentally, why?
Because we're missing, if we model them statically, we're missing the key effects like this direction dependence.
If there are no further questions, this concludes the public session. Let's thank Peter one more
Right.
time. Oh, sorry. I'll sit down.
Okay, so not gonna lie, I'm looking forward to this part of my defense for a long time. I get to thank everybody who helped me along the way. You guys should get comfortable, it's gonna be on a long. So first up was Bill Chick. Bill is brilliant, super hardworking, amazing communicator, really inspiring leader, and a ridiculously good fundraiser. So he really does everything well. When I first joined the group, Will's reputation was to be the best in the world at what you do by the time you graduate, which to be honest I thought was pretty ridiculous. But Will makes it possible by setting such a world-class example for us to look to. Will, it's been such a privilege working with you for the past 5 years. If I could sum up your impact in a few words, I'd say that you brought out the best in me. You set a really high bar that's way out of reach, and you helped us get there. And moving forward, I'll try to do the same. I'll try to bring out the best in others, just like you've done. That said, I have to use this picture. This is me and Will at Yang's wedding. Will is definitely a hot mess. To be honest with you, we both had our relationships. This is probably a bit more accurate. I'm really fortunate to have such an all-star committee. He is really a legend in the battery field. It's really humbling to have him on the committee, and I've enjoyed working together for the past year on the Cryo-EM work. Mike is really a world-class expert in X-ray characterization. Also really enjoyed our scientific discussions. Foucault studies structural battery designs as well as acoustic monitoring of batteries. Simona studies battery management systems, going beyond the cell level to even the pack level. I haven't formally worked with Foucault or Simona, but I've really enjoyed learning more about your work from papers and talks. Thanks again to all of you. I'm looking forward to this session. I'm also really fortunate to have had the opportunity to work with a lot of other PIs, and a lot of this is testaments to Will's hard work in setting up the batteries. Richard Bratz does the machine learning work. He has a really incredible knack for detail, which has really gone a long way in my work. I worked with Martin Mazzano on a number of projects. Martin's probably the world leader in continuum scale battery modeling. And so I'm really happy working with him. Stefano co-led the OE work. Really enjoyed working with Stefano. He has this really healthy pessimism that counterbalances well as exuberant optimism really well. And last is Steve Pierce. Steve is a battery scientist working at Berkeley. In a lot of ways, he's been like a second advisor to me. Steve was very generous with his time, so when I first joined the group, I knew nothing about batteries or SEI or anything. And Steve spent a few hours on the phone with me every week, teaching me sort of what he knew about SEI. Steve's also very creative, outside of the box, and he doesn't take himself too seriously, which all these things kind of make him a lot of fun. I'd also like to thank my student collaborators from other groups, Super and Kristen at MIT, as well as Lohan and Attia here at Stanford. Somebody recently asked me if I knew the secret for graduating on time for the group, and I think the answer is actually pretty simple. It's just by having great confidence. Actually, almost all of my papers have been co-first authored papers. I think in academia, this is sometimes seen as a bad thing, which I think is a real shame because I think in all cases the whole is a lot bigger than the sum of the parts. Each of them taught me something I knew very little about before. I'm really grateful to work with all of them. I also need to thank two collaborators of mine from within the tree group. First is Norman. I spent a lot of time with Norman working on a lot of different projects. Some of them may never see the light of day, but Norman is super logical. There's just a lot of times where he helped me think clearly about projects and problems I couldn't see clearly myself. He's also really hardworking and a real team player, and I think he's really responsible for a lot of success in machine learning work. Next is Jerry. Jerry's a master's student that I mentored. I haven't cleared Jerry's a collaborator with a bunch of PhD students because a lot of what he really contributed at the level of PhD students. And one other thing about Jerry is that he's almost always smiling. He almost always makes me smile. So he's also a true pleasure to work with. Next up are my mentees, Nick, Mike, Steve, and Jerry. These are the 4 undergraduate and master students with the pleasure of working with for the past few years. All of them brought a lot of youthful energy and enthusiasm to their projects, which really helps speed things along. And they're also really do a lot of success in machine learning as well. These guys also served as guinea pigs for my mentorship abilities. I'm really grateful for their patience with that word how to become an effective mentor. And it's cliche, but all of them, I'm sure it's happy as leads most of that time. There's also a lot of other people to thank. Special shout out to TRI guys, Patrick Morat, for all the dirty work behind the scenes to sort of get the machine learning pipeline up and running. I also especially like to thank the material science staff, Fee, Mark, Tricia, Andy, and Monica. I bought a lot of stuff, and they mostly helped me stay out of trouble while doing it. I'm happy that Tricia was able to make it out today. Thanks for being with a colleague. Also, I thank my funding sources, Toyota, Ford, the Stanford Pre-Court Institute, for project funding. I forgot about a lot of stuff, and these guys paid for it. I'd also like to thank NSF and SGF for scholarship funding. Next up is the True Group. The True Group has changed a lot over the years since I first joined the group. The top picture is from my first group retreat, and as you can see, just a year later, it really started growing a lot. This is the most recent photo, probably 2/3 of the group from 2018. And given that we've taken like 10 students since our dinner, I think this is probably But actually, the True Group has really been one of the biggest highlights of grad school. The True Group is very sharp and talented, but I think the traits that stick out the most are their helpfulness and support. Whenever anybody needs help with anything, there's at least 3 people like immediately ready to help. I just learned a lot from so many different people. Special shout out to some of the senior battery segment members like Yie, Wiljen, Antonio. They set a really high bar for battery work. Also had a ton of fun with the True Group, between group retreats, conferences, group hikes, random nights out, and even weddings. And I'm really glad I get to call some of you friends. Next up is Stanford friends. I'm really grateful to have a lot of you in my life. Some of you kept me sane, others of you made me a bit more insane. Trying to get all balanced out. The picture on the top right is Nick eating 14 saltines. I think I can honestly say it's been one of his smarter ideas in grad school. But thanks to all of you for my Stanford experience. I also want to give a quick shout out to the Delaware friends that came out and visited me. I know some of you may be watching online. You've been to year definitely really helped with my initial homesickness. Next up is family. Kind of go from cousins, aunts and uncles, to grandparents, to in-laws, especially to my brothers. Thank you all for your love and support. Today I really want to thank 3 people in particular. First up is Victoria, my wife. Before I say too much, I need to thank her as an experimental collaborator. I think 2 or 3 times she helped me load cells late at night when no one else was but actually, Tori's just been incredibly supportive throughout my PhD. There have been just so many times when I told her I need just 10 more minutes. 10 minutes turns into 2 hours. She took it all in stride. Tori is very patient, helpful, easygoing, very big-hearted, adventure buddy, and best friend. Something Tori's grandma always tells me when I talk to her is that I bundle out of my knowledge. And I she's right. Tori, thank you so much. I love you. I could have done that. Then my parents. It goes without saying, my parents have been there if you need some say one. They've also always supported me unconditionally, while also setting a high bar for education. My dad is the original Dr. Attia. He's the kind of doctor that actually helps people, though. It's such an honor to be able to follow him. I know moving out to California hasn't been super easy for you guys to adjust to, but thank you for supporting me throughout it. I've learned and grown so much from this experience. Mom and Dad, thank you. I love you. This thesis is dedicated to you. The very last thing I want to talk about is my faith, my Christian faith. We've talked about this with a few of you before. And for me, nothing gives me more peace, purpose, or joy than this. I think this quote summarizes my position well. Not where I ought to be, not where I want to be, but still not where I once used to be. By the grace of God, I am what I am today. All right, I warned you guys it's going to be long. Thanks for Now it's really fun.
Hey, he's leaving. You can get his money back.
Oh, hey, how are you? Hey.
Yeah, sure. I really don't need any more.
But like, doing it in normal. Okay. Yeah, not bad. Are you still around here?